having seen certain physical properties like ionization enthalpy, oxidation states and electrode potentials, now we will see the next set of physical properties which are there, which is mainly regarding the magnetic properties, how it works as catalysts, interstitial compounds, formation of alloys and many other things. So, let us first talk about the magnetic property of these compounds. So, what are the magnetism that are being present in these D block elements? Let us see. So, magnetism is nothing but attraction of species around, and that is being split up into diamagnetism, paramagnetism and ferromagnetism. Now, first we need to understand what are these properties. Diamagnetism indicates no magnetic properties with them. So, if there is another compound coming near it, it will not have any attraction towards itself. Whereas the other two sets of compounds, which is paramagnetism and ferromagnetism, they will attract by the magnetic field that both the compounds generate. And some examples of it, copper and gold happen to show minimum magnetism, whereas iron and nickel, they show maximum magnetism, and that is why we believe that they are strongly attracted by the magnetic field. So, no doubt at the outset in the physical level we saw what is diamagnetic, paramagnetic, ferromagnetic and all, but from chemical point of view, how are we going to design this magnetism properties? So, that is defined by a system where a scientist named as Bohr brought out a formula which is given as mu is equal to root of n into n plus 2. So, the unit of that was called to be Bohr magneton, and what we need to understand here is what does this n mean, what does this mu mean. N indicates the number of unpaired electrons only, it does not mean the paired electrons, that has to be very clear with us, whereas mu indicates the overall magnetic movement that is possible in a compound. Let us for a simple example understand the magnetic properties say of manganese. Now, manganese, when you write the oxidation state or the electronic configuration, it is 3d5 4s2. Now, 4s2 is thoroughly paired with itself, but the 3d5, as you know by various rules of chemical formations, has 5 unpaired electrons in this. So, if I have a manganese metal study, the number or the value of n is going to be equal to 5. So, this is how the value of n is being recognized in these cases, and all these calculations are done. The final answer is given by Bohr magneton. So, moving forward, let us now see some of the other examples that are possible where a single unpaired electron will have this magnetic properties. In this case, the value of n will only be equal to 1, and this is determined by the spin of the system. Now, this is more like a theory of earth revolving around the sun. Now, we know very well that a year has 365 days, a day has 24 hours, but what happens in that is there is some object at the center which we take it as sun, and this earth is something that is revolving all around it. And this earth will have its own spin, that is what gives us day as well as night. So, in this case also, these electrons which are there, they move around the nucleus which is present, but at the same time they keep spinning around itself also. So, this spinning nature is what gives it the magnetic attraction. If it is paired, it is stabilized by itself. But if it is unpaired, it likes to see some attraction with other atom. Suppose this is one and the other one with an opposite spin, if it is there, it would like to attract each other. So, this is how the magnetic properties of the compound can be determined. So, moving forward now, this was one such example in the case where a couple of examples they have shown you, where if you take n is equal to 1, which means 1 unpaired electron, n is equal to 2 indicates 2 unpaired electrons, the following calculations which are shown there gives you the overall magnetic moment of that compound, and the unit called there is Bohr magneton. So, as a case study, let us study for all the possible ions of these elements. Generally, we study with respect to ions because ions are the one which form compounds in nature. So, the very first example that they have taken Sc3 plus, scandium 3 plus. So, what is the condition of this scandium 3 plus? That let us see. We know very well scandium has an electronic configuration of the argon being present inside and then followed by 3d1 4s0. Now, if it is in +3 state, we realize that 3d is also 0, this is 4s2, and 4s is also 0 because 3 electrons have been removed out. So, when you remove out, when you use this formula of mu is equal to n into n plus 2, there is no unpaired electron available at all. So, the value of n will be 0 and 0. When I just try to substitute this will essentially become 0 Bohr magneton, which means that there is no magnetic property associated with this ionic form of scandium. So, whenever there are no n values, n becomes 0 whenever there is no unpaired electrons. So, just when we go back to that table now and see all the properties, there are some calculated values and observed values, and we know very well that the practical observation will not be 100% in sync with the theoretical parts. So, theory is using a formula, trying to find out the answers, and that answer is given in that calculated column, in the 4th column. But the observed ones will more or less be near to it. It may not be perfectly in sync, it will be more or less, and here there are some examples. Calculation is absolutely easy. Just identify the electronic configuration, identify the configuration of that particular ion. For example, let me talk about the chromium +2 ion that is considered in the table. So, if you see the 5th element in the table that they have shown, so we know very well that chromium is 3d5, 4s1, this is due to half stability case. If it is chromium +2, the first electron goes from 4s, second electron goes from 3d, and when you consider these parts, how are the 3d electrons present? We know that they are all present in the first place as singly. So, what is the value of n here? N value is going to be taken as 4 into 4 plus 2. So, when you see in that table, this is the n value that they have considered, and with that n value, the final calculated value has been observed in these cases. So, this is how the entire table will give you a cohesive idea of all the compounds that are being present. So, you are able to see that in that Cr +2 state, the configuration is 3d4 and 4 unpaired electrons are shown there. Moving on further from this magnetic property, there is another property that these compounds show, and that is the formation of colored ions in this case. When we recall the first year chapter of structure of atom, we realize that the color of the compound is generally considered where if this is a lower energy condition which is there, and if this is the higher energy condition which is there. So, if an atom or electron is present here, you need to supply energy so that this goes top. This atom or electron which is present here needs supply of energy so that it can go to the higher excitation state. Now, can it stay in the higher excitation state for all the time? Definitely no. It will stay only till it has that energy and it comes back down. Remember that you had supplied energy while taking it up. So, this energy is given out now in the form of color and it comes back to the lower oxidation state. So, what is this energy is formation of the color. Now, this is possible when electrons go from one energy state to another energy state which is higher, and while coming back they will give out the energy which is present. So, let us see certain factors for this color of the compounds. Generally what happens here is these compounds, they are able to absorb a color and they will transmit the complementary color of the compound which is there. So, this is only possible if there are free electrons, because if it is paired they will be perfectly stable by themselves. They do not want to go to higher state and all that. Only those who are unpaired, they can go for a higher state and again return back. So, this is just a practical assessment of what these compounds are, you can see some are colorless, the starting and end part of the table. In between you have various types of colors. Now please realize that the colorless ones are those which have 3D0 and 3D10. All other conditions are definitely giving you some sort of color. Now the question here is, generally when we talk about stability, D0, D5, D10 we take it in one condition. But here D5 is giving color, D10, D0 are colorless. D5 is giving color because in D5 you will find unpaired electrons which are present. So this colors you need not memorize it as such, but the basic thing that you have to know here is that if there are unpaired electrons, it will not show color. If there are paired electrons, it will definitely have a property where this pairing electrons cannot excite higher. So only those which are unpaired, they will show some color properties. This is just a pictorial view of that. When we form various solutions of the compounds, blue, green, all this sort of colors are possible, and that color is only obtained when you see the second figure now. You have a red radiation light which is coming, which is actually absorbing, and red color, complementary color is seen to be blue. This you study in the optics of physics that you study. So if red color is absorbed, it will give back blue color to the natural eye. If blue color is absorbed, its complementary color, red color, will be given. So that circular part actually gives you an idea of which are the absorbed colors and complementary colors. As an example, they have taken a copper solution here. If you remember in your laboratories, whenever you find a copper compound, it is blue in color. Now that is because red color is absorbed and blue color is given out, which is complementary in nature. So seeing the color of the compounds, now let us talk about the catalytic properties that are been there, and this catalysis is possible because these compounds, we have already studied that they can have variable oxidation states, they have large surface area, and as examples a couple of catalysts are shown there: vanadium oxide, iron in the manufacture of ammonia, which is actually the Haber's process which we have studied in our earlier classes also. And nickel is used in hydrogenation of oils. This was also used in the conversion of alkynes, alkenes into alkanes. So catalytic properties for these compounds are possible because these compounds have a property where they can keep on changing their oxidation states. So you are able to see various oxidation states that are possible now in this case. So what we understand by this is, these D block elements, and in that specifically 3D elements, they have this property of regularly changing the oxidation states. Observe the example that is given there. Two reactions are shown. In the first reaction, we are able to see that Fe3 plus is getting converted into Fe2 plus. Similarly, in the second reaction, we are able to see that Fe3 plus 2 plus is getting converted into Fe3 plus. So once again, if you see that reaction very clearly, in both the reactions, they are termed Fe ions to be catalyst. What is the role of a catalyst? Take part in the reaction, do the required adjustments in the ionization case, and it comes out as it is as a metal. So in the first reaction, 3 plus to 2 plus state indicates that it has gained an electron. In the second reaction, another electron is lost, which is going from plus 2 to plus 3. So losing of electrons, we can call it as oxidation, but then this acts as a reducing property. So here, what we understand by these two reactions is, ions can adjust itself in such a way that it can act as an oxidizing property as well as reducing property, because it can fluctuate between plus 2 to plus 3 and plus 3 to plus 2. So because of such a fluctuation, we can realize that they can actually act in both the cases as oxidation as well as reduction conditions. So these are certain important catalytic properties which we see. Once again, we will just see some more examples here. Hydrogenation of oils utilizing nickel, Haber's process that we discussed, where iron is used as an catalyst in that condition. Some more examples like copper sulfate, platinum, vanadium pentoxide in the contact process, preparation of sulfuric acid, nitric acid which is there, which actually is called as Ostwald's process. So here we use platinum or rhodium as a catalyst. All these are part of the D block elements. So this is how they help in acting as very good catalysts. Then we have a certain set of compounds called as interstitial compounds. Now what are these interstitial compounds is? These are compounds where generally the formation of these compounds will have strong structural parts which are there, and whenever we write the structure like this, the problem with this is you definitely see some small spaces being present in that. So these small spaces which are there, if you leave it open, it may not form a stable solid structure. D block elements, because they have varied oxidation states, they have the small gaps present between them. So to settle in that gaps with stability, we know that in the air we have carbon, nitrogen, oxygen, so many gases which are there. So these gases actually come and occupy the small spaces which are there. And that is why these type of compounds where 3D elements are present, but they are also having a combination of small elemental forms like carbon, oxygen, nitrogen, we call them as interstitial compounds. So what are some properties of interstitial compounds? That let us see. So these compounds are non-stoichiometric. What is the meaning of this word? This was the very first chapter for you in first year PUC. Stoichiometry indicates perfect combination of compounds. So in the example, if you see, titanium is combining with carbon, then manganese with nitrogen, especially the last example, vanadium with hydrogen, but they tell that hydrogen is 0.56. What is the meaning of this? We haven't come across this anywhere till now. So that 0.56 indicates that vanadium as a metal keeps in 0.56 ratio of hydrogen in the small spaces which are present in these conditions. So this is about the interstitial compounds, and because they have the small elements, there are good number of compounds which have high melting points. They are pretty much stable in these cases. So these are some properties that are there: high melting points, they are pretty hard, metallic conductivity, and chemically inert because they have already reacted with compounds like carbon, hydrogen and all. So they will not like to react any much further, and they will be inert, meaning that it will not react further. So just a pictorial view of this interstitial compounds which are there, where as I told you that gaps which are there, the white color systems are the atomic forms of the D block elements. The yellow color balls that you see is nothing but these small carbon hydrogen compounds which are utilizing those spaces. And as examples, you can see some very good solid items like titanium carbide, titanium nitrides and all, which can give good solid screwing items for our daily usage. The next set of properties in this is alloy. This is something that you have studied in your earlier class, where alloy is a homogeneous mixture of couple of metals combining together. Now this has to be homogeneous. It can't be that just copper will be on one side, iron will be on another side. No. This has to be a complete composition where it will give rise to new type of compounds, for example like brass, bronze, which is a combination of copper, zinc and copper, tin, brass and bronze. So what it does is it gives better properties for the compounds. Now if you use just pure copper, the problem is, it will not have a perfect resistance, it will corrode off very easily, and then you can't supply very high amount of heat. But the same copper, with utilizing that copper, if you make brass or bronze in combination with zinc or tin, you can see that these alloys will have a better strength. You can make it into different possible shapes. It will not have a very high mass because it has combined and utilized all the available spaces that are being present. So this is how alloys give you a very important segment in these cases. So let us see some examples of these alloys which are there, where we can classify these alloys into ferrous alloys and ferric alloys. So in this ferrous and non-ferrous systems, one thing becomes clear that ferrous alloys are those which will involve iron, non-ferrous will generally be devoid of iron. And if you see some examples there for non-ferrous alloys, they have shown aluminium, then aluminium bronze, magnesium, brass, bronze, all this form non-ferrous because there is no iron content in that. Whereas in ferrous alloy, it is a combination of iron and carbon. If the carbon content is a little high, we call it as steel. If that is low, we call it as a general iron alloy. And along with this iron, you may have some small elements like chromium, vanadium or tungsten. So this is just an overview of all the uses that are present of these compounds. Stainless steel we generally use it at our home for utensils. Automobile parts are being made of that. We have various other compounds like nickel, steel, Invar metal which is there. This is mainly used for instrumentations of compounds. So we need meter scales, pendulum, clocks. This Invar steel which is there is a major component of these compounds. They have also given some composition systems of magnesium aluminum combination. Generally the non-ferrous systems they are used where it will be helpful that it does not undergo corrosion or other aspects of this. So this is an overview of the general uses of the compounds that we tend to see. So this is all about the physical properties that we come to know about these compounds, and with these physical properties we can use these compounds in various segments that are present in our day-to-day life. So having seen all these parts now, let us just look into certain homework of this. Let us try to revise certain parts of this in these segments. This is just a pictorial representation now. Interstitial compound versus alloy. See what is the difference between these two compounds. Interstitial compounds are having atoms, and in between the atoms they have tried to squeeze in that yellow color things which is nothing but carbon, nitrogen and other things. Whereas alloy it is the same atomic form where some blue balls are replaced by red balls, which means that homogeneously one compound is mixed into the other forms. So this is about the interstitial and the difference in the alloy formations which has been present in these cases. So let us look at some questions now. Give an example for an alloy. We have just now discussed this part. Which 3D element has the highest oxidation states? Please go back to the concept of oxidation states and check out how best you can form the oxidation states. You can think over this. Calculate the magnetic moment of a divalent ion in aqueous solution if its atomic number is 25. So as an hint, first write the configuration of the atomic number 25 which is actually manganese. Then form a divalent ion. What do you mean by divalent ion? Make it into +2 state. And then try to calculate with the N value that you get. And the final question, what is an interstitial compound? We have discussed a lot of this, but maybe you have to put it properly into English statements of this. So this is all that we have for this segment in this place, and with the further segments we will see about the compounds which are present for our general day-to-day uses as oxidizing agents. Thank you. Sai Ram.